In this session, we're going to review the ARIMA forecasting model. The objectives for today's session are to look at the differences between an ARIMA model and an ARIMA model, define stationary time series and identify its importance, describe and identify autoregressive and moving average processes, and then define the differences between random walk series and white noise series in an autoregressive or AR series. So let's start with defining what a stationary time series is. A stationary time series is characterized by the following features. It is stochastic, which means that it's governed by randomness, so there's not a pattern to it. There's a constant mean, and there's a constant variance. ARIMA models can be used to model stationary time series, and ARIMA X models can be used to model stationary time series with exogenous variables. The X stands for exogenous variables. So we'll see what that means here in a minute and how we go about doing that. So this is a visual for stationary data. So here we have a constant of mean of 30, and we can see that it's random about that mean of 30. So you can also see that the variance is constant. Therefore, this meets the criteria for a stationary data set. A non-stationary data set includes the following characteristics. There is a discernible pattern in the mean of the data across time, such as a long-term trend or some seasonal components. And there is a discernible pattern in the variance across time, so it could be increasing or decreasing in variability over time. So if we see these elements, then that time series would not be stationary. So let's look at an example of a non-stationary data set. Here we can see that the overall mean, but then there's an upward trend that we see in this data set. So this would be considered a non-stationary data set. And so let's talk about how we can handle this. For this type of data set, we're going to use an ARIMA model, and so let's define what that means. AR stands for autoregressive, and that is the current values are going to be related to the past values. The I stands for integrated, so that means the different values between successive points is models, which makes it stationary, and we'll see how this is done here in a little bit. But here the integrated portion is an attempt to actually create a stationary data set. Basically, there's a pattern across the time periods. And then MA stands for the moving average, where the current values are related to past estimation errors. And that is going to be some of our previous shocks. So I want you to note that ARIMA models are special cases of ARIMA models or series that do not require differencing and hence do not require the integration. If a time series is non-stationary, it's going to be customary to transform it to make it stationary before we begin the modeling process. If the transformation is differencing, then you can call the model ARIMA or ARIMA X if you're using exogenous variables for that integration that you perform to back transform your forecasting to the original time series value. So let's look at an example here for our first differencing. Here is a time series data set with income. So a lag would simply just be moving this forward the value from one period into the forecast of the following period. So for the 2005 prediction, we use the 2004 value. The differencing is the difference between these two. So the 2005 value minus the 2004 value is the first order difference here. And we end up doing that throughout the table to end up populating the last column. Now, if you visualize these first order differences, this is what we see. And so here we have our mean, which is represented by that red line. And now we can see there is some element of randomness to this data set, unlike what we saw before, where there was a trend. So now, when we did our first order differencing, we now see what appears to be a stationary data set. As a reminder here, the I stands for in ARIMA stands for integrated and tells you what order the data was difference to convert it to a stationary process. So for example, the first order difference is order 1. Starting with a stationary series, you will use an ARIMA model on the original series. Then you will start with a if you start with a non-stationary series, you have to first transform that data to create a stationary process, and then you'll use the ARIMA model on that transformed data series. So let's look at exactly what we're doing here. It's just regression. So here's our model for ordinary least squares regression. You should all be familiar with this by now, where you have y equals beta 0 plus beta 1 x plus e. What we're trying to do with an autoregressive order 1 model is we're trying to predict y at time t as a function of beta 0, and the prior value we observed for that y. So at y at t minus 1. And so this is what it looks like once you put it in terms of a time series. And again, we always have that error term at the end as well. So this is a graph showing our fit for this specific example when we fit a time series ARIMA model here. And this would be the fitted line for our ARIMA model. So again, remember why we're using a time series model to begin with. One of the assumptions that we have with a regression model was that the errors are not autocorrelated. So what we're doing when we are doing this first quarter differencing is we end up with this type of data set now. And now, once we have done that, we can actually create our models. We're no longer having errors where there is an autocorrelation. But we have to go through some sort of transformation phase along the way to achieve that. But in the end, the ARIMA model is nothing more than a regression model where we're taking some additional steps so that we can achieve the assumptions that are required for regression or present. So let's look at the process flow for the ARIMA model. So you begin with a stationary series, and if you don't have a stationary series, typically what we will do is we will take a differencing. That's the I, or the integrated portion of the ARIMA model. And then you examine the autocorrelation function plot, and we'll talk more about that here in a little bit. But if you recall from prior lessons, there is a plot where we can view to evaluate whether we can observe autocorrelation in the data itself. And then you can perform a formal test for white noise, the Ljung-Box chi-squared test that we discussed in our last session. And then we decide if the time series is white noise. So if yes, then tough luck. There's really not anything you can do about that because there's not really any systematic variation in your series. Your best guess is just going to be the mean of the series, and that's all you have. We have to have some level of signal to be able to predict a future value. So if it's not white noise, that's excellent, because then we can look at the systematic variation in the data, and we can model that using an appropriate ARIMA model. So how do we determine an autoregressive order? First, we need to confirm that the series is stationary and contains autocorrelation. We want to determine which lagged values, which is yt minus 1, t minus 2, and so forth, are correlated with the current value yt. And then we want to adjust for the autocorrelation of all the lower order lags. And we'll talk more about that here in a little bit. And then for that, we also want to look at the partial autocorrelation plot, the PACF, which helps us to determine the autocorrelation by answering the following questions. Is there significant autocorrelation between yt and yt minus 1? Is there a significant autocorrelation between yt and yt minus 2 while holding autocorrelation between yt and yt minus 1 constant? So, we're going to be isolating the other correlations for that specific lag to see what holding the rest constant and whether there's going to be, in fact, an autocorrelation on a particular given lag. So let's look at the visual here. If we see significant spikes in the PACF, those spikes are going to be the most important source of information for identifying an autoregressive series. So, when we see the biggest spike, those are the most important ones for us to evaluate. So going back to the kilowatts generated from the earlier example, and we look at the PACF plot, we see that only one lag was significant. And we can see that it was above the 95% confidence interval for the PACF. Therefore, we only need an autoregressive order 1 for the specific model. Now, looking at the picture on the right, we're looking at sales. We can see that there are 3 points that are significant. So what we are seeing here is, unlike the autocorrelation plots, the autocorrelations do not spill over from one lag to the next, but rather they hold constant at all of the lower order lags. This helps us to identify the lag order structure that we need to use. So to summarize, what we're looking at, the kilowatt hours generated, we see that it's only as significant at lag number 1. So we just need an AR order 1 or autoregressive order 1. But for this one on the right, we are looking at a partial autocorrelation for sales, we see that 3 of them pierce that 95% confidence interval. Therefore, we want to use an AR3 autoregressive 3 type of model. So now let's talk what this looks like. So here's a first order autoregressive model, AR1. And for this, we are setting YT equal to a function of the prior observations. So YT minus 1, okay? YT is a function of that previous value plus some error. Now, what is a first order moving average? Okay, in this case, YT is a function of the immediately previous shock plus error, meaning that the error of what we see in the prior observations is correlated to our YT value. So again, the YT and the error at t minus 1 are correlated, and we're incorporating this into our model. So to summarize, in an autoregressive model in AR1, we are effectively including the prior observation, and that is effectively leading to our current prediction. So for a moving average, the first order moving average, we are incorporating the error in the last prediction plus some shock to help us predict YT. So let's look at this moving average bit a little bit more. A moving average model is a function of past shocks going back Q periods, so however many you go back. And so in this case, it could be eta sub t minus n. So n could be any given period or lag that we're looking at. Our past shocks are uncorrelated with other past shocks. So that is one of the things that we are making an assumption on. Unlike the other autoregressive models, the moving average models are going to be used to model short-lived abrupt patterns in our data. And forecasts after Q periods immediately revert to the mean of the series. So again, it just looks at the short-lived abrupt patterns in the data and is incorporating those into our Y sub t forecast. So moving averages are going to be the sum of our stationary processes, and as a result, the pure moving average models are always going to be stationary. And the time series containing autoregressive and moving average variations are called ARIMA models. So in this case, there's an autoregressive component, and then there is a moving average component. Then, if we integrated, that is, we took the difference, then that is the I for ARIMA. Otherwise, we just have an ARIMA model. So again, the three components of ARIMA, you will typically see it denoted by P, D, and Q. So the first, you have your autoregressive order, which is your number of lags that you'll be including. The example of the kilowatt hours was an example of an autoregressive order 1. But when we looked at the partial autocorrelation plot, or the PACF plot for the sales example, we saw that it was ordered 3. And so now if we need to create a stationary data set, then we would need to do differencing. So that would be the I portion of ARIMA. And then the MA is the moving average order, which would be our Q value. So again, ARIMA models are ARIMA models with D differencing equaling to 0. So that will be denoted by P and Q only. So this will be a typical structure we would define when we're setting up an ARIMA model. What is my P value? What is my D value? What is my Q value? So as far as evaluating the accuracy versus fit, we're typically going to be using information criteria to compare how all of our models performed to the data. And the examples for this would be AIC and SPC, which is just a form of BIC. So again, Bayesian information criterion, the Schwartz information criterion, and the Akane information criteria. Accuracy statistics are used to evaluate the forecasting error in either the fit sample or the data that is used to build the model. And that is our holdout or test sample. And again, if we have enough data, we will always want to have a holdout sample, as that will be a better indication of how well the model is going to be generalizing. Another thing we want to do, similar to regression, is evaluate the residuals. Here, we are going to want to assume that the residuals are white noise and that there's not a pattern. So this is not different from looking at regression, because in fact this is regression, and we're going to assume that the errors are centered at a mean of 0. There with the constant variance, they're going to be normally distributed, and that will be independent. We also want to have the independence of errors as well, so we don't have any autocorrelation in our errors. And here we can also evaluate the white noise assumption, which again, the assumption being that the errors are random by looking at the means of the errors, the variance of the errors, and the independence of observed values at different times. So here we are just looking at the correlation diagnostics for sales, and we can see the autocorrelation plot. There's nothing significant past 0, so that is good, right? We can see here more clearly with the PACF partial autocorrelation block. And so here there's nothing that is piercing that 95 confidence interval. So overall, it is indicating that we do in fact have no autocorrelation, and all the residuals themselves are completely random.